Hello and welcome to this presentation related to integration applications. There are several previous presentations related to this topic area where we use integration to calculate areas under curves, volumes of revolution, centroids of area, RMS values, etc. In this particular presentation we're considering what are termed miscellaneous problems where we calculate the volume of a cone in a thermodynamic context, calculate the work done under a PV diagram, and also calculate the volume of a hopper in the form of a rectangular frustum. It should be noted these questions are particularly difficult, indeed I found them quite challenging, but I hope the detailed work solutions included here will help aid your understanding. Indeed you may find your own more preferable solutions to the problems. For reference, here's a slide from our previous presentation. On the left hand side contains the integral table we've reviewed previously. On the right hand side shows the laws and the rules of indices, sometimes used to simplify our expressions. Just note within this presentation we'll just be using selected extracts from the standard integral table and from the indices table. Presentation overview. Essentially the presentation consists of 4 questions extracted from my notes. For each question we will show the full work solution as in this video. So question 1. So part A. This relates to a cone having a base radius capital R and vertical height capital H. We have to develop a formula for the cross-sectional area at any height, lowercase h here, measured from the tip of the cone. Once we've derived the formula, we then have to use this formula for the area and derive a formula for the volume of a cone in terms of the radius lowercase r and the height lowercase h using the process of integration. Lowercase r, lowercase h are the variables in this problem. Question 2m. The top and bottom of a hopper that's shown in the sketch are horizontal rectangles. We're given the dimensions at the top of the hopper and also at the bottom of the hopper, and we're told the vertical depth or height of the hopper. So initially we have to develop an expression for the area of the horizontal cross section at any vertical height, measured as x, shown here on the diagram on the bottom of the hopper, and then we have to find the hopper's capacity in meters cubed. So essentially part B will integrate the expression formed in part A. Similar process to that involved in question 1m. Approximate start times related to question 1m and question 2m, but please note these times are rounded to the nearest minute. Presentation overview continued. Question 3m. This relates to a thermodynamic context, calculating the work done under a PV diagram. In part A, we're given that the mass expands by the law PV is equal to C, is a constant. And given the information in the question, we've got to derive an expression for the amount of work done, capital W, in terms of pressure P1, volume V1, and the expansion ratio V2 divided by V1. So we'll solve this using the process of integration. Next, we're given that the mass expands to the law PV to the power n is equal to a constant. And again, given some information in the question, we've got to determine an expression for the amount of work done, capital W, in terms of P1, V1, P2, V2, and the index will power n. Again, using the process of integration. And then finally, question 4m. The first part, we've got to obtain the expression for the length of an arc and also for the area of a sector having a radius of r and included or subtended angle d theta. Second part, we have to determine firstly the length of an arc and secondly the area of a sector, radius r and included angle theta. And finally, by considering a circle of radius r as a particular case of a sector and thus have an included angle 2 pi, we've got to derive a formula firstly for its circumference and secondly for its area. And here are the approximate start times related to solutions to question 3m and question 4m. These are particularly difficult solutions and further hints are stated within the presentations. So let's now consider the solution to question 1m I will briefly repeat the question here, but if you prefer you can move directly to the solution, commencing on the following slide. So part A cone has a base radius of capital R, a vertical height, capital H. We've got to obtain a formula for the cross-sectional area at any height, lowercase h, measured from the tip of the cone. Part B, so now using the formula for area from part A, we now have to derive a formula for the volume of a cone in terms of radius, lowercase r, height, lowercase h, using integration. In the square bracket here we have the answer for part A, for the area, and for part B, the volume. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now, but I'll show you the appropriate diagrams to construct on the next slide. Here's question 1M, commencement of the solution. Here are the appropriate diagrams to commence the solution. Left hand side we have the cone, that's base radius capital R, maximum height capital H. And notice lowercase r is the radius of the cross section at any distance lowercase h from the tip of the cone. The right hand side shows our elemental strip, considered here, thickness dh at height h from the tip, and the radius of the elemental strip is r. Note angle theta shown here, angle of the cone from the centre line. Remember part A, we have to find a formula for the cross-sectional area any height h from the tip of the cone. So we need to generate two equations here, both related to the tangent of angle theta, one in terms of capital R and capital H, one in terms of lowercase r and lowercase h. We rearrange the equations to find lowercase r in terms of h, and then knowing the formula for the area of a circle, area is equal to pi r squared, we can obtain our formula. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now, with a full work solution shown on the following slide. So question 1M, solution continued. Here's part A, obtain our expression for the area in terms of height lowercase h. So step 1 here, from the sketches shown on the previous slide, one of which is repeated on the right hand side here, we can form an expression for tan theta in terms of r, capital R the maximum radius, and height h, capital H the maximum height. Remember that tan of the angle is the opposite side divided by the adjacent side, so that's the capital R divided by h. Label that as equation 1 for reference. And we can do the same for tan theta, but this time in terms of lowercase r and lowercase h. If we rearrange this equation for r, multiply both sides by h, so r is equal to h multiplied by tan of angle theta, for that equation 2 here. We can then substitute equation 1 into equation 2, so the tan theta now replaced by the capital R, capital H, so multiplied by lowercase h. So now we've got a formula related to lowercase r. We know that the area of a circle is pi r squared, so now we simply replace the value of r, this expression here from above, and then simply squaring the bracket, we find our formula for area in terms of lowercase h. That's part A concluded, the expression for the area at any height h. So we've essentially calculated the area of this cross-sectional strip here for our cone at height h from the tip of the cone. Just notice, and this is purely for reference, that if we measured height h from the base of the cone, our formula for area would be this expression here on the right hand side, still in terms of height lowercase h. Question 1b, solution continued. So here's now part B, we're determining the formula for the volume of a cone. So volume, capital V, is the area derived on the previous slide for the elemental strip. Here's the formula derived, multiplied by dH, so the area of the circular cross section multiplied by dH is the volume of the elemental strip. Here's dH in the integral, and that's integrated between limits of 0 and h, 0 this point here, capital H this point here. Lowercase h is measured from the tip of the cone in this case. What has happened on this next line is I've taken the constant outside the integral. The constant is pi multiplied by r divided by h, or squared. So that leaves me with lowercase h squared multiplied by dh. That's my integral. That standard form is ax to the n form, referring to our previous standard integral tables. So integrating x squared with respect to x becomes x to 3 divided by 3. So in this case, integrating h squared with respect to h becomes h cubed divided by 3. And integrating the question 1, we use the ax to the n format from our tables. Item 1 shown here. Ax to the n integrates to ax to the n plus 1 over n plus 1. All we do now is insert the limit. So insert in the upper limit, the square bracket shown here is h cubed, and insert in the lower limit, in this case is 0. So evaluating, we determine that the volume of the cone is calculated from the formula pi r squared h divided by 3. And again, that's a standard formula you will see in any textbook or reference book related to calculating the volume of a cone. So that concludes the solution to question 1m. Question 2m. The top and bottom of a hopper are horizontal rectangles, as shown in the sketch on the right hand side here. The longest side of the top rectangle is parallel to the longest side of the bottom rectangle. The top rectangle measures 10 meters by 8 meters, shown here, 10 meters, 8 meters at the top. And the bottom rectangle measures 6 meters by 4 meters, shown here. The sides of the hopper are plane, it's two-dimensional, and the hopper has a vertical depth of 8 meters, shown here. Part A of the question, we have to obtain an expression for the area of a horizontal cross-section at a vertical height x meters from the bottom of the hopper. So from the bottom of the hopper we measure dimension x, and this shaded area highlighted in the sketch is the horizontal cross-section for which we have to determine the expression as a function of x. Part B of the question, using the expression derived in part A, we then have to find the hopper's capacity, the volume, in meters cubed, and that's using the integration process. The answer to part A, the expression is shown here, and the capacity here is shown in meters cubed. A very large capacity because of course the dimensions of the hopper as given are also very large. I would encourage you to stop the presentation and attempt question 2m, but the full solution is shown on the following slides. Question 2m, commencement of the solution. This is part A. We're trying to obtain an expression for the area of the horizontal cross-section at the vertical height x meters from the bottom, the base of the hopper. So the area we're considering is this cross-hatched area shown highlighted in our sketch. So to find the area of that section, it will be essentially b multiplied by d, but what we need to do is to determine an expression for both b and d in terms of a function of x. So bottom of the slide here, I tried to indicate some side views of the hopper. So the left hand sketch here relates to the side of the hopper having a base of 6 meters and a top dimension of 10 meters. So that's this side shown here. And the second sketch here relates to the side of the hopper having a base of 4 meters and the top dimension is 8 meters. So in each of the sketches we have our dimension x commencing from the base of the hopper. Notice this dimension here is labelled as y1 and this dimension here y2. What our aim is here is to have an expression that allows us to calculate the width of the side at any position of x. Taking the left hand diagram, the base of the hopper is 6 meters, the top of the hopper is 10 meters. We want to know what the dimension of the hopper would be at position x. So what would be the dimension of b and what would be the dimension of d at location x. Of course the overall height of the hopper was given as 8 meters. So this sketch shows our geometry related to the angles and the dimensions we are given, and on the next slide I'll show how we use these sketches to develop the expressions required. Question 2M, solution continued. There's still part A here. Let's obtain our expression for the area. So from the previous sketches, of which I've shown on the right hand side of the slide here for convenience, we can determine the tangent of angle theta. In our geometry here, it's angle theta. And for the tangent ratio, that's the opposite side of a right angled triangle. That's 2 meters shown here, divided by the adjacent side of a right angled triangle, and that's our 8 meters shown here. So the tangent of the angle theta is simply 1 upon 4, or 0.25. And that's the same for both sides of the hopper, because in both cases tangent of angle theta is 2 divided by 8. Let's consider dimension B, shown here on our sketch. And dimension B would be 6 meters, that's its dimension, plus twice of dimension y1. Here's dimension y1, and of course that dimension is the same on the right hand side as the left hand side of our sketch, so that's why it's 6 plus 2 times y1. If we now consider the relationship for y1, we can also write tangent of angle theta in terms of y1 divided by x, shown here. Rearranging dimension y1 with simply x multiplied by tan theta. So replacing y1 with x tan theta, and then replacing tan theta with 1 upon 4, tangent ratio from above, we can form an expression for dimension B in terms of x. Question 2, solution continued. So by a similar process, dimension D is 4 shown here, but in this case plus y2, and y2 shown here, and of course will be the same on the left hand side. As on the previous slide for y1, we can show y2 is equal to x multiplied by tan theta, so replace y2 with x tan theta, and again we know tan theta is 1 upon 4, it's a quarter, so we can evaluate an expression for dimension D, again as a function of x. Back to our sketch here, this is dimension D at location x above the base of the hopper. So now we're in a position we can find the A here. So area is equal to the dimension B from the previous slide, multiplied by dimension D here, and then inserting the appropriate expressions. Notice this is a binomial expansion here, so we have to expand the brackets using our, for example, crab claw method we reviewed in a previous presentation. We expand the brackets, collect the like terms together, and finally we can show that A is equal to 24 plus 5x plus x squared divided by 4, but I also showed that as an alternative form of 24 plus 5x plus 0.25 x squared if you want to remove the fraction from the expression. So now we have the expression for area of our cross section at some height x from the base of the frustum. We'll now be able to integrate from 0 through to h, the total height of the hopper, to find the capacity or the volume of the hopper. Just note for reference, this bracket here is erroneous to the solution. And that's part B of the solution. So question 2M, solution continued. So part B, we'll now determine the capacity or the volume of the hopper. So it means we need to integrate over our range of x, which is from 0 to 8 meters. So to work out the volume, that's simply the area of the elemental strip multiplied by the thickness of the elemental strip, which is considered to be dx. So cross-section area times thickness is the volume. If we integrate that between the limits of 0 and 8, we will find the total volume of the hopper, and that's the capacity of the hopper. So from our previous slide, part A of the solution, we have the expression for area, so integrating 24 plus 5x plus x squared divided by 4 with respect to x between our limits of 0 and 8 meters. I'll let you undertake the integration process and the simplification. And as in the previous question, we're using ax to the n format for the integration process here. So 24 integrated with respect to x is 24x, 5x integrated with respect to x 5x squared upon 2, and x squared upon 4, integrated with respect to x, becomes x cubed upon 12. So our limits back of the bracket here. So inserting the limits into the integral and evaluating, the volume is approximately 395 meters cubed. So that's the solution to question 2m. Here's question 3m. We're given that if a pressure, in our case P, is exerted through a small increment in volume, labelled delta V, then the work done is equal to P multiplied by dV. So part A, given that a mass expands such that PV is equal to a constant C from an initial condition of pressure P1 and volume V1 to final volume V2. We're asked to derive an expression for the amount of work done, capital W, in terms of P1, V1, and the expansion ratio, V2 divided by V1. In part B, we're given now that a mass expands such that PV to the power of n is equal to a constant gained from initial conditions of pressure P1 and volume V1 to final conditions, pressure P2 and volume 2. We've got to determine an expression for the amount of work done, W, in terms of P1, V1, P2, V2 and N. Answer to part A of the question shown here, answer to part B shown here. So essentially to solve these problems we have to integrate the given expression of P dV, so we're integrating P with respect to V. Given the information in the respective parts A and B, we'll be able to derive an expression for P in terms of V by rearranging the given function, case A and B, and then we'll integrate the expressions between the limits of V1 and V2. And as a hint to help you solve part A of the question, so to show the final answer shown here, after the integration process, you will need to use the relationship constant C is equal to P1 V1. So once the integration is solved, by inserting P1 V1 for constant C, you should then be able to prove the answer shown for part A. As a hint to help you solve part B of the question, determine the final answer shown here after the integration process, you will need to use the two relationships shown here that I've labelled C1 is equal to P1 V1 to the n and C2 is equal to P2 V2 to the n. So after you've integrated, you'll have constant C, but if you consider to insert a C1 and C2 for C in the appropriate places in the derived formula, you should be able to prove the answer shown for B. I made it sound slightly more complicated than it is, but hopefully using these two substitutions, you'll be able to solve for solution for part B. I'd now encourage you to stop the presentation and attempt questions 3M, both parts A and B, but I'll show you the full work solutions on the following slides. Question 3M is the commencement of the solution in part A. So we have to calculate the work done, given the relationship PV is equal to C. Calculating the work done essentially means determining the area underneath this diagram here. Here's our expression PV is equal to C. Limits of our calculation would be V1 to V2. So given PV is equal to C, labelled as equation 1 for reference, and noting from the question that the final solution must be in terms of P1 V1, shown here on the slide. We will ultimately need to use the relationship P1 V1 is equal to C. Call that equation A, again for reference. So to commence the solution, the first thing we need to do is to find P as a function of V. So rearranging equation 1, P is equal to constant C divided by volume V, over that equation 2 for reference. So now we can calculate the work done. W is the integral of P dV, essentially given in the question, between the limits of V1 and V2. So now I simply insert equation 2 into the integral, so replacing P with C divided by V. On the final line on this slide I've simply brought the V from the denominator to the numerator, that's why it's V to the negative 1 now, and I've taken the c outside of the integral because it's just a pure constant. Now I'm ready to integrate v to negative 1 with respect to v between the limits of v1 and v2. We'll undertake the integration on the following slide. So question 3m, solution to part A continued, just repeated equation 1 and equation A from the previous slide for reference. To integrating v to negative 1 with respect to v, that becomes ln v. That's item 6 here in our standard integral table. X and negative 1 integrates to ln x. So we have v to the negative 1 integrates to ln v between our limits of v1 and v2. Our next line we simply impose the limits, so the upper limit and the lower limit. We have ln v2 minus ln v1. That can be written as ln of v2 divided by v1. That forms equation 3. Just for your reference, here's application of the second law of logarithms. Log of a minus log of b. That's our ln v2 minus ln v1. The fact we're using natural logarithms is irrelevant. Remember, the laws of logarithms apply to any base. And using the second law, that can be written as ln of a divided by b, where a is v2 and b is v1. So we end up with the equation c multiplied by the ln of v2 divided by v1. Now in this case, to find the solution, we're simply going to insert now for constant c, equation a shown here. So we end up with the solution of w, work done, is p1 v1 multiplied by the ln of v2 divided by v1. That's substituting equation A into equation 3. So that's the solution to question 3 part A. That's the solution for part B. Again, we've got to calculate the work done, but given the relationship pv to the power n is equal to c. So that's my equation 1 in this case. And because the final answer is given in terms of p1, v1, p2, v2 and n, shown here on our slide for part B, I will need to make use of this relationship p1, v1 to the power n is equal to c, for that equation A, and p2, v2 to the power n is equal to c, for that equation B. The actual process in the solution is very similar to that of part A. Firstly, rearrange the equation 1 for p, so that's c divided by v to the power n this time, equation 2 here for reference. And commencing again with the same integral, and again we're calculating the area under the PV diagram shown here. This time it's PV to the n is equal to c, and the limits of our integral are the same, v2, v1. But inserting equation 2 into our integral, we replace the p with c divided by v to the n. Again, as with part A, we bring the volume from the denominator to numerator. So this time it's v to the negative n, and we take the constant outside of the integral. So now we're ready to integrate. Solution continued on the following slide. For question 3m, solution continues, part B. So integrating v to the negative n. This is item 1 in our integral table. Integrating ax to the n this time. And the solution is ax to the n plus 1 over n plus 1, shown here. And our limits are still v1, v2. So next line, imposing the upper and the lower limit. What I've done on the next line, just slightly simplifying the expression, that's all. The next line is simply multiplied the numerator by the constant c. So c shown here, c shown here. There's an expression for work done, equation 3. But now to determine the final answer as given in the question, I will now have to replace the first constant c1 with equation A, that's shown here, the p2, v2, power n. And replace the second constant with equation B, p1, v1 to the power n. Notice now that the v2 to the power n numerator here cancels with v to the power n numerator here, leaving with p2, v2. And for the second term in the square bracket, we now have v1 to the power of n divided by v1 to the power n. So that leaves us with p1, v1. So we now found the final answer for work done, as required by question 3, part B. Here's question 4m. Part A, we have to obtain expressions for, in one here, the length of an arc, Item 2. The area of a sector of radius r, included angle delta theta. Then part B, we have to determine for part 1 the length of the arc, and part 2 the area of a sector of radius r and included angle theta. So in other words, in part A of the question, we develop our expressions, but in part B we will integrate. Part C, by considering a circle of radius r as a particular case as a sector of a circle with included angle 2 pi, we have to derive a formula for, first of all, its circumference, secondly, its area. So again, that's an integration process required. Answers to part A and part B, shown here, and answers to part C, shown here. If you think you can attempt this question without further information, I'd encourage you to stop the presentation and do so now, but I will show you some hints on the following slide, should you need some help to commence a solution. In question 4M, part A, is the hint for the solution. We're going to apply radian measure, s equals to r theta. So here's a sector of a circle, arc length is ds, radius is r, and the angle subtended or included here is d theta, and that's considered a very, very, very small angle. Imagine it's very, very difficult to actually measure angle d theta. So now can you develop the expression, first of all for the arc length in terms of r d theta, and then for the area of the sector in terms of radius r and included angle d theta. I'll show you the full work solution on the following slide. Question 4M, solution here for part A is part 1. Is our expression for the arc length ds is equal to r d theta from radian measure. Part 2, we can now calculate the area, I've called it dA, the area of the small sector. And to do that, we need to consider the right-angled triangle shown here, which has a base of length r and a height of r d theta, assuming here that d theta is a very, very small angle. That's why we can make this assumption. So calculating standard formula for area of a triangle is base r multiplied by vertical height r d theta. That's all divided by 2. The expression for the area of the sector can be shown to be r squared d theta divided by 2. Question 4M, solution continued. This is for part B. Now we've got to determine firstly the length of the arc and secondly the area of the sector of radius r included angle theta. So we're now going to integrate the expressions derived in part A. Question 4M, solution part B continued. So here's the solution for part 1. Calculating the arc length, we're going to integrate from s is equal to 0 through to s is equal to s1, left hand side of our equation. And on the right hand side, s is equal to r d theta between the limits of 0 and theta 1. So integrating ds with respect to s, that becomes s. If it helps, think of this as 1 multiplied by ds. And on the right hand side, integrating r with respect to theta becomes r multiplied by theta. In both those cases, we're using item 1 from our standard integral table. They're both ax to the n format. On the left hand side, we have 1x to the 0, 1s to the 0, that helps you, integrates to s. On the right hand side, we effectively have 1 d theta, so again that integrates to theta, in this case multiplied by r. Imposing the limits, we can clearly see that s1 is equal to r theta 1. The lower limit, of course, is 0 here. And part 2, to find the area of the sector, shown here. We now integrate on the left hand side dA, or 1 dA, between the limits of 0 and a1. On the right hand side, we integrate the r squared d theta divided by 2, between the limits of 0 and theta 1. Notice that r squared upon 2 is a constant, so that can be taken outside of the integral sign. So we're simply left with the integral of 1 d theta between our limits. So again, if it helps you, think of there being a 1 here, and of course there's a 1 here. So on the left hand side, integrating 1 with respect to a becomes a between our limits. On the right hand side, integrating 1 with respect to theta, that becomes theta. to our limits. Imposing the limits, we can see that a is equal to r squared theta 1 divided by 2. Finally, question 4m, solution continued, part C. Again, we're going to use radian measure, s equal to r theta here. So we're now considering a circle of radius r, where the angle subtended, included here, is 2 pi. Here's radius r and angle 2 pi, 1 revolution. We're going to use radian measure to derive the formula for item 1, the circumference of the circle, and item 2, the area of the circle. Full solution is shown on the following slide. Question M, solution continued. In part C, I'll let you review this slide at your own pace. Essentially the circumference, s is equal to r theta, where r is r, and theta is 2 pi, so s is equal to 2 pi r. That's how you calculate the circumference of a circle. Using radian measures, essentially the arc lengths. And part 2, calculating the area. Area here is r squared theta 1 divided by 2. Theta 1 is now 2 pi, so that simplifies to area is equal to pi r squared. We should be able to recognise the formula for circumference, often expressed as pi d actually, but it's 2 pi r here, and the area of a circle often stated as pi r squared. Here's the bibliography used to help generate the presentation, which I hope has been of interest to you, and thank you for viewing.